Alright, so what I'm going to cover in this video today is how to do a between subjects one-way ANOVA in R, going through data screening, effect size, power, and pictures. So this is sort of a complete example of how you might do a one-way ANOVA using R. But for sure, it is only between subjects. So each person is in a different group and they don't overlap, and a one-way design. So that means that there's only one independent variable. So the first thing we're going to do is import the data. And I'm going to go over, again, how to import things from SPSS, because a lot of people who are learning R are trying to switch. And so if you have SPSS data and you don't want to open every single file and save it as a CSV, importing it is important. So I'm going to use the MIMISC library. I like it a little better than foreign. So if you don't have that one loaded, be sure to install it. You can also use the foreign library. So what you can do is I'm going to save my data set as master data. And the way you do this is as data set, I believe, but I got my notes saved here just in case I couldn't remember. So it's as.data.set. Which is a different type of object in R that I don't know that it's used as frequently for the types of things that we're doing. Then it's SPSS system file, and then I'd come up with the file name. So what this part does is it allows me to import SPSS files, and this sort of converts it into something we can use in R. Otherwise, it does not import as a usable object. So let me set my working directory to where I have this file saved. So I can just call it the name of the file. Oop. So that's where my SPSS file is saved. If I click on files over here, that did not go to my working directory, but here it is. I have a bunch of stuff. But I also have my chapter 10 ANOVA example.save. So be sure you spell this exactly how it's spelled. And that should import the data set. Okay, so this is a formal data set, which means that I can't do a whole lot of some of the analyses that I'm interested in. I can't necessarily use that type of R object. So what I'm going to do is just convert the data set to a data frame. And that will switch it to what I'm used to working with, which is a data frame. You can't do as.data.frame here. I've tried that. It doesn't work. Okay. So the MIMISC library will never give you an error like foreign does, but it does require an extra step, although it's not too hard. Okay. So first thing we want to do is just kind of check for accuracy of our data. So this is the data screening section. And so I'm going to check and see if my data is accurate by taking a summary of the data set. So I have a fake data set on the number of Cokes a person drinks a day, because I'm trying to cut back on the number of diet sodas I've been drinking. And so they have none, 1 to 2, or a whole lot of Cokes. So I'm trying to stick to myself in the 1 to 2 category. And I do have some missing data, so we'll deal with that later. And then I have how much anxiety a person has based on the number of Cokes that they're drinking, because maybe that much sugar will make you nervous. Okay, so the minimum is 2 and the max is 19. So let's say our fake made up scale here is from 0 to 20. So the data would be within range, and I have some NAs, but nothing weird going on in this category. So my data is accurate, and I would move on. Okay. If your data isn't accurate, you should watch the data screening video to talk about how do I deal with inaccurate data. So the next step in the data screening process, go from accuracy to missing data. And we clearly do have some missing data. And so I can see that by just looking at the summary here. So I have some NAs. But I'd really want to know what is the percent of my missing data. Now, I don't really have any missing data in something I would want to fill in, but I do want to just show you the percent missing formulas. Okay. So I'm going to call this percent miss because I'm going to make up my own function. So we're going to start by making our own function. So the function of x is, and then now I'm going to calculate missing data. So I'm going to use is.na of x. So that will allow me to total what are the number of NAs, right? So when it hits an NA, it'll say yes, that'll give me 1 point. I'm going to sum all those up. So sum up all the missing values, and I'm going to divide by the length of that vector. And so that will give me the sum of all the missing values divided by the length. So that's the proportion of NAs. And then I want to multiply by 100 just to make it a percent. It's a little easier to read. Okay. So that's our own little made-up function to be able to calculate the number of missing values. Okay. And what I want to do is do apply. Okay. So the apply function allows me to work on rows and columns. And so I'm going to take my master data set. So apply needs the data set name or column name, data set name. And we're going to first calculate by columns. So how much missing do I have by columns? And I'm going to fill in my %miss function. Okay. And so let me just add some little notes here. So that first thing tells me I have 5% missing in my Cokes column and none in my anxiety column. And so if Cokes was actually a column that I wanted to fill in, I probably could. It's close to 5%, but remember the rule is about 5%. Let's look at by people now. So exact same code. So master 1 for people, so by rows, and then my %miss function. And that's not very useful. So you see lots of numbers. So that's by person. So I'm going to just call that missing. Okay. And I'm going to take a summary of the missing data. Oh, no, sorry. Table. The table function would be better. So I have 168 people who are missing no data and 9 people who are missing 50% because there's only 2 columns. And so I probably want to exclude those people because I don't really want to guess what Coke group they're in. And that's 50% of the person's data. So if we're going to go with a fairly stringent criterion of only filling in 5% across and down, we probably wouldn't want to fill that in. Okay. And so I just want to exclude missing data. Okay. So I don't have to use the mice library. If you run the mice library on this data set, it would fill in those 9 participants, but if you were first to exclude the missing people who are missing too much, that's everybody. Because I don't have anyone who's missing 0 to 5% to fill in. Okay. So I'm just going to exclude them and not use my missing data fill-in function. Okay. So let's do this as no missing. So I'm going to take my master data set, and I'm just going to use the subset function because it's pretty easy. So subset, you tell it what data set you want to use, and then I'm going to say anybody whose missing value is less than 5, less than or equal to 5. Okay. And that will definitely exclude these missing people here. Okay. Now that might get grumpy at me. Did I do it in the wrong order? Yeah, okay, so it'll be, these have to be less than or equal to. Okay. So that should have excluded some people. So we have 168 people. So it deleted 9 folks who are missing 50% of their data, which is way more than 5%. So we've handled missing data. Now let's talk about outliers. Now I've talked in my other videos about outliers in a multivariate way using Mahalanobis distance. That will not work on this data set. So I can't really be an outlier on my Coke variable because that is a quasi-experimental variable. It's a naturally occurring group. And they're not really outliers on that. That's what you're interested in studying. So we really just want to see if anxiety has any outliers. And so I can take a quick look at the anxiety variable. Okay, so make sure you're using the data set that you just created. So keep using the data set as you go. Don't go back to the original. Okay. And it doesn't really look like I have any outliers, but maybe some of them are based on the mean. And since I only have 1 column, Mahalanobis distance won't run because it requires at least 2 columns to create the covariance between columns. So in this sort of sense, because I only have 1 DV, I need to use z-scores. Okay. And so I'm going to create a z-scored anxiety column by using the scale function. And that means I need to do no miss, $, anxiety. Okay. Now, I didn't z-score the column in the data set, and then I also didn't add it to the data set. So I just created myself a new vector, a new little mini data set of the z-scores. And that way when I am brain fart, I am deciding to exclude people or not, I don't have to drop that column from the data set. So it's just an extra column that I can use as a screening criteria, but it's not part of my data set really, because this is only data screening. Alright, so let's look at the z-score column. So the great thing about Studio is it'll let me sort. Okay. And the rule is 3. Okay. So we want people to be greater than an absolute value of 3. And so these two are pretty close, but they're not quite there. And then I have some here at the top that are also pretty close. If I wanted to exclude these two as sort of close enough, I could. So what I could do is say no outliers and let's do that same subset function. Okay, so I got, we're going to subset the no miss data set by looking at z-scored as less than or equal to, and let's do this. Let's do absolute values, so ABS, so we don't have to do 2 criteria, greater than 3 and less than negative 3. Less than 3. That will create me a new data set, but it didn't exclude anybody, right? Because I set the rule to 3. If I set the rule to 2.89 instead, that would exclude 2 participants who are at the very top here. They're very close. And so that's a decision that you can make. And you can change your mind later by going back and changing this criteria. Okay. Now, I bet those people are on the bottom of the distribution because they have the lowest scores. And so that was likely why they would have been excluded, because their scores are significantly less than the mean. So it's probably these people down here. So we could try with and without those participants and see what happens. And that would tell you whether or not they had a huge effect on the mean as being close to being outliers. And so we can try that here in a minute, but right now I'm going to keep using my real criterion, which is 3. Okay. So I don't have any outliers. I have some that are close. Now let's get into assumptions. Okay. So the first assumption is additivity. So we don't need to check that. I have one dependent variable, so there are no correlations to check. Okay. Then we would move on to normality. Okay. But before we do that, we sort of have to set this up. And so to do that, what I'm going to do is create myself a fake variable because we could screen this using a linear model, using the function we're going to use, using the formula, that we're going to use. But let's say I want to kind of screen both variables together and see if people's combinations of variables are strange for normality and homogeneity and stuff. So let's... and that might create, when I have categorical groups, what I'm trying to say is it might create you sort of 3 little clumps of data. So let's see what happens. But if you ever get a piece that has 3 clumps of data because you've screened both the IV and the DV at the same time sort of together, you can go back and just screen the DV and see if that is what's causing that issue. So let's see what happens. So I'm going to set this up by first creating myself a random variable. And I'm going to do that with the R chi-square function because the errors should be randomly distributed. Right? And so to do that, I have to tell it how many do I want. So in row of my no outlier data set, so the number of rows, my degrees of freedom, 7 is sort of the magic number that I've used for a long time because it works. There's no other reason. So I've set up this random variable, and what I'm going to do is create my fake regression using the random variable we just created, so LM, it's random, approximately the entire data set, which I can use with a dot, and then data equals no out. So that will create me a random regression using both variables. So I'm going to screen the IV and the DV, and you could just screen the DV, that's fine, and we'll see what happens. Okay, so remember that the dot here is run this with the entire data set. So I'm going to use both variables to predict a random distribution. And then therefore the errors for this should be random and normally distributed. when they're standardized. The other two things we need to do for the setup is create a set of fitted values. Okay. So I'm going to create a set of fitted values by pulling those from my fake regression. But to make life easier, we're going to scale those. So we're going to z-score them just so they're more interpretable. The other thing I'm going to do is create a set of standardized residuals. And that's the R student function of our fake data set. Okay. And that gives me my standardized residuals from the regression. Okay. Now, to check normality, since I only have one DV, I could actually just look at the histogram of that DV. It's pretty easy. Okay. That's actually what I already have pulled up. And it looks really normal because this is made up data. So I'd say the data is pretty much normal, but if I wanted to check on this in a multivariate way, we can use the, the wrong function here. So I could also take a histogram of the standardized residuals. So those should also be normal. And they're pretty close. Okay? Now remember, this includes our grouping variable. So you might get little clumps of data. So if you see kind of a multimodal distribution, try changing your regression to be only the DV. Because it might be that each distribution is slightly separated, because that would be the point of an ANOVA, is to show that the three groups have different means, so they'll therefore have different standardized residuals as well, so you might get little clumps. And when that case happens, just make sure that try going back here and changing this to just the DV and see if you get a better picture, okay, which I'll do in here in just a second. So I would say it's pretty normal. Let's do linearity. And that's the QQ norm plot of your standardized residuals. Okay. And then we're going to add AB line 0, 1 to give us a line to check this on. And I'd say it's pretty linear. Not so much up here. This is the outer limits of standard deviations. So this is 2 standard deviations. So I'd say it's pretty linear, not so much on the tails. It is hard to make things to be linear on the tails, but most of the data is pretty close to the line. Okay, so this is a little troublesome. Now let's see what happens if I do homogeneity and skedasticity. And so that is a residual plot. So I'm going to do the plot of my fitted values on X and my standardized residuals on Y. And then I'm going to add a 0, 0 line to see where they cross at 0, and then actually add a vertical line as well to give myself some quadrants. So one problem we have is that this does not really appear homogeneic, because it runs from 0 to 3 this way and 0 to 1 this way. So on this end, this is not so hot. Because we don't have the same spread above and below 0. Now most of the data is in this 2 to maybe 2 range, but this is beginning to be an issue. So I'm going to check Levene's test to tell if this is really a problem. Okay, from this direction it's pretty good. Okay. Now homoskedasticity is I draw a circle around the dots, and that's a nice big blob. So that one's okay. It's not making a triangle shape in any form. And so my main concern appears to be homogeneity, and maybe a little bit of linearity. Now, if I wanted to do this without the IV, so I just want to screen the DV for these particular problems, what I could do is change here. So let me leave this one in here. So this would be screen all the variables. And then this one would be more akin to what we're doing with our data. So, no, it's still anxiety. Oops, spelling. This would be screen only the DV. Not known for my spelling. There we go. So the cool thing about R is now I can just run this exact same set of stuff and see what it looks like. So it's looking roughly the same. Okay. So the problem apparently is with the DV. Okay. Oh, except for this. Here's a great example of heteroskedasticity. Look at this triangle shape that it's making. And so that's problematic. Okay. So here, So great picture of what heteroscedastic might look like. But when we include the IV, it's not. So maybe this is a grouping issue. Alright, so I really want to check Levene's test, because my normality is still a problem. And so this is still technically part of data screening. And so we're going to use a library that I'm not going to remember. I think it's just straight in R. Brain farts. So let's check, make sure I don't have... No, it's in CAR. Okay. I knew I was forgetting something. Oop, wrong one. Okay. So Levene's test is in the CAR library. Okay, so let's load that up. Okay. Most R installations come with CAR, but if you don't have it, it's a great library. It has lots of cool stuff in it. So Levene capital T test is a way to check if the homogeneity of variances has been met. And so what we're going to do is set this up like we do a regression. So it's going to be Y, so anxiety, is predicted by the number of cokes you have. So this is the real analysis now, not a random one. And we're going to tell it where the data is. Right, so in my no outliers data set. And that gives me Levene's test down here. So, oops, and I centered it on the median. So we also want to include center equals mean because we're doing an ANOVA, and our model is the mean. Okay, there we go. So it's not that different, but it is an important distinction to make. So looking at Levene's test here, I really want to look at the p-value. This is an assumptions test, so we want to make sure that we're using the data screening rules, which is 000, so a 0, 0, 0, and 0, 0, 0, it didn't happen here, it's greater than that value, so it's okay. It's actually greater than 0.052, and that, remember, it's a distinction that's more the traditional Tabachnik and Fidel style, and if you're using the Andy Field book, he's going with 0.05, both legit, just make sure people know which one you're doing. I fall on the, it needs to be really crazy before we change our data set side. Sorry. Okay, so Levene's test isn't an issue, so I'm going to keep going with a traditional test because I also have way more than the 30 people. That's in the normality rule, but ANOVA is fairly robust to violations of different assumptions. It'll still give you the same answer as if you would run its counterpart non-parametric statistic. Okay, so let's run the ANOVA. I'm going to use the AOV function. I'm going to save this output for reasons we'll get to in a second. So AOV. And then it's the same setup as here. Okay. So let me make sure I'm not forgetting anything. Haven't lost my mind. Nope. Cool. So, I got y is approximately x, data equals no out. Okay. Now let's take a summary of that output. Okay. Now the AOV function is a special type of the LM function, just like ANOVA is a special type of regression with categorical predictors. And so what the AOV function does is it allows you to get a summary output that is in the same style as what you're used to seeing in a summary table, which is how most people teach statistics, myself included, and that's what you might see in SPSS or SAS. And so it just creates you a different set of output than what the LM function would show you, although they're literally the same math. Okay. So it shows me my degrees of freedom for my model and my error. So residuals, it does not show you the total, but that's okay. You can add them together and get the total. My sum of squares for both. My mean square, which is divided going across here. And then my F value. I think most people put sum of squares first, but it doesn't really matter. So this is a significant test. So I'd want to maybe look at why it's significant. So where is it significant? If your homogeneity of variances is not met, you can use the one-way.test function, which will do a Welch correction. And it's the same exact formula. And so not assuming equal variances, it's not quite as pretty, and it still would be significant. So even if we wanted to correct for homogeneity issues, if there were any, it would be 0.04. Okay, so there is a quick way to correct. We didn't really have any homogeneity problems, so I'm going to stick with the traditional ANOVA, but if I did, this is how I could fix it kind of easily. Okay. Now, let's calculate effect size. And I'm going to calculate R squared, but instead of just doing the math by hand, which would be sum of squares model over sum of squares total, and I can kind of show you how that would work. So we do 65.7 divided by 65.7 plus 1412.6. Okay, so I'm just adding here. And so let's see what R squared is. Okay, 0.04, so that would be a small effect size. The other thing you can do that's kind of quicker, summary.lm of my output. Okay, and that switches it back to the linear model summary. So this is the output you would see if you ran this as an LM, which gives me the same F values, overall model values. It doesn't really show me the rest of the sum of squares and degrees of freedom part. And then it actually shows you the coefficients, so you would interpret this in a traditional regression style. And this is actually very similar to doing a post hoc, but that's neither here nor there in this video. We'll talk about this more when we get to regression with categorical predictors, and then go back to, well, this is just ANOVA. But the cool thing is that it does give you multiple R squared. So I got 0.044, which is the same output I got here. Okay, so this is a little faster and I don't have to remember the formula. But it is sum of squares model over sum of squares total. That's actually the exact same thing as eta. So you can use R squared or eta because they are the exact same formula. I don't know why we have two of them, but we do. If instead you want to calculate omega squared rather, I will admit to not knowing this formula off the top of my head because I so rarely use it. I will get the formula from my cheat sheet I have open. Okay. So the formula for omega for between subjects one-way ANOVA, so this only applies to this particular design type, is sum of squares model divided minus degrees of freedom model times mean square residual. That's important. So let me get my summary out of the original one here, and let's see if we can fill these in. So sum of squares model, that's here. So I got 65.7 minus degrees of freedom model, that'll be 2, so right here, times mean square, so MS residual, so 8.56. Now, I'm going to divide that whole thing by sum of squares total, so I got to add these together, 65.7 plus 1412.6, so that's a very similar denominator as to up here, right? So we're subtracting out some of the residual, so that means this number will be smaller, and then dividing by something similar on the bottom, but we're also adding in this mean square residual, so 8.56. Well, let's see what that is. So omega will always be smaller because you are subtracting out some of the variance, and so we got 0.03. So still a small effect size. Sometimes they can be quite different. In this case, they're not terribly different. So that would be effect size. So let me break here and talk about power. If I can remember how to spell G power. There we go. Alright. So I don't know what I did to make G power not be full screen on my Mac, but awesome, because often it's cut off on the end of Macs. But anyway, so under test family here, we're going to select F test, because this is an ANOVA. Under statistical test, we're going to come down to fixed effects omnibus one way, which is between subjects ANOVA for a one-way design. Okay. And then the problem is that this effect size F here is Cohen's F, and that is not a formula that most people know, so let's hit determine. I could type in all the means and the sizes and it would calculate for me. Instead, I'm going to select effect size from variance here, and then direct, and it'll let me enter eta squared. Partial eta squared and eta squared are the same in a one-way design, so I'm going to enter 0.044. And let's see how many people it would have suggested us to use with that small effect size. So calculate and transfer to mean. So that gave me 0.2, right? And so alpha, we're going to set at 0.05. Power, we're going to set at 0.80. The number of groups is the number of levels, so I have 3. So it would have suggested that we needed 213 people. So I don't quite have 213 people, so I think technically I'm a little underpowered. Even though we found a significant effect, we don't have enough people that it would have suggested we use. Okay. Now, usually you'd do this at the beginning, but I'm just giving an example with numbers that we've already calculated. If you aren't sure what to guess here, because this is before the test, if you hover over it, it will give you some examples of a small, medium, and large. Okay. Or you can take what you've found in the literature and guess from there. Alright, so that's how you do power for one-way designs. So we did power here. Now, since we found a significant effect, what we have to do is a post hoc test. So post hoc tests allow us to figure out where the effects are. So we have a significant omnibus test, the overall test, but now I want to know what happened where. And so I want to see if there are differences between our Koch's groups. So the first thing let's do is just get some descriptives. So I'm going to calculate my means using the tapply function, because now I have a variable I want to split on and not do rows and columns. And so tapply, first thing I want to do is say no out, it's dv first, and then an iv, Koch's, and I want to calculate the mean. So let's see what our means are. Okay. So our means looks actually like it's none is high anxiety, 1 to 2 is lower anxiety, and then many Koch's is back to high anxiety. So I bet none and many are not very different, and maybe these two are different from 1 to 2 here. So that's sort of interesting. It actually creates sort of a U shape. And so we might find that this data is quadratic in nature. And so maybe the people who are getting to drink one of their Koch's are not quite as cranky as people who aren't drinking any Koch's. Okay. Let's do standard deviations, because we'll need those to be able to report this data. So it's the exact same code. SD at the end. Okay. So SD. And here are my standard deviations. So that's why homogeneity and variance was okay, because they're roughly equal. And then if we want to know what the group sizes are, you can actually use the table function, but creating them in the same structure as your other ones, if you wanted to calculate standard error, is has its advantages. So we're going to use the length function. So the table function will tell me the exact same thing, but since these all have the same data structure within them, now I can create standard error by doing standard deviation divided by the square root of n, because I have them in the same structure. So I could actually get the standard errors as well for our groups using this sort of procedure. So that's one reason why I suggest tapply rather than the table function, but just a warning, you could do it both ways. So I could report now standard deviations or standard error with my groups. I'm going to make a picture here in a minute, but now that I've looked at the descriptives, I have a good idea of what might happen in my post hoc tests. Okay. All right, so let's try those post hoc tests. Okay. Now, there are 4 different sort of types of post hoc, or not even post hoc, because that's the name of a specific one, follow-up tests. So let me call them follow-up tests here. And so there are orthogonal contrasts, sort of planned comparisons. There are a priori that you can do. I'm not going to cover those. There are post hoc analyses, or a posteriori analyses, that are, I want to compare everything to everything else. Sometimes they're called pairwise analyses. And there are trend analyses where I can see if there's a trend in my data, which makes sense with a sort of quasi-linear or continuous effect. So my none to 1 to 2 to a lot is sort of a linear variable. And then we could just do lots of t-tests and skip the ANOVA altogether. And so one reason why you wouldn't want to do lots of t-tests is because that inflates the type 1 error rate. And so with 3 tests, that's 0.14. And that formula is 1 minus alpha, which we're going to set as 0.05, because that's the traditional value, to the, so use the little caret icon above the 6 on a traditional keyboard, number of comparisons. So we've got 3 comparisons. How did I know that? Well, it's 3 comparisons because it's 1 versus 2. Or here, I'll use the real names. So none versus 1 to 2. And then we're going to compare none versus many. And then none, 1 to 2 versus many. Okay, so that is all the pairwise combinations. So doing them 2 by 2. And so I have 3 of those, so it would be to the third. That means the type 1 error rate is 0.14. So I can't just do a bunch of t-tests because that would inflate my ability to make an incorrect rejection and say things are significant when they're not. So now I have to do some sort of follow-up test and a correction. So I really want to get into the distinction between, and we're going to do post hocs. So the post hoc test is a t-test. In this case, it's an independent t-test because this is between subjects and ANOVA. And that's the traditional thing to do, is say some type of t-test. However, there are corrections. And that is what I'm going to go over. So I could do no correction. I could do a Bonferroni. I could do a, and let me just make this distinction. No correction is sometimes called an LSD for least significant difference. I could do a Tukey, which is sometimes called HSD, honestly significant difference. We're going to talk about student Newman-Cools, or S&K, and Scheffe. Okay. There are lots and lots of post hoc tests. There's a really great Sage book, the little green book by Toothaker, I think. I don't see it on my shelf here, but about post hoc tests and how they work, if you're interested in post hocs. So that's just an important thing to me, is for you to understand that the test itself, the statistical test, is actually a t-test. The correction on that test, which corrects in different ways for different tests, is the Bonferroni. So don't tell me you ran a Bonferroni. What you ran was an independent t-test with a Bonferroni correction, or a dependent t-test with a Tukey correction. So getting that. Tests are still independent t, but the correction is how we fix this type 1 error problem right here. I cannot spell this, so I'm going to come over here and copy it. What we're going to load is an agriculture library because it has lots of sweet post hoc test options. And I'm going to show you all the different combinations with the caveat of only do one of these. But since this is a demo video, I want you to see what all the different options are. Okay. So the first option is basically none. So it's kind of an LSD test, which just makes me laugh. Okay. So let's do LSD. And we have to do that on the output we saved earlier. So that's why we saved it. Okay. The second part of this, it's LSD.test. Okay. So the first data is the saved output from your ANOVA, your AOV function. The second one is what variable you want to use. Well, I only actually have one in this case, it's Cokes, but this is the label of your IV variable. So when you have multiple IVs, you can actually pick one or the other here. Okay. We're going to turn off the group function so that we can see the tests, and then turn on the console function so we see what we are interested in. And that combination just gives me the mean differences in p-values, which is what I'm mostly interested in. You can try turning those off and on and see what they do, but that combination is what I was interested in. So this LSD test is no correction. So this is running 3 independent t-tests. We'll look at the output here with no correction. So the cool thing is this gives you so much information. I really love this library. I'm glad I found it. It's pretty new, I think. And so it tells me the means here. So I know I ran those means up here in t-apply, but I got my means and the standard deviations actually right here. This little r should actually be n, so that is the n value for those. So this set of descriptives was really just for me to explore, but I actually get all those values right here. I do not get standard error, so if you wanted standard error, you could take SD here divided by n, or you could do this little function. It gives me the lower and upper confidence interval for my mean, and then the min and the max. So this is beautiful. If this had standard error, it would be the best thing ever. It tells me what alpha value I'm using, and my critical t value for that alpha, and my degrees of freedom. So that's nice. This gives me like what the criteria was for this test. And then as we scroll down here, you'll see this is actually where all the magic happens. So it compared every difference to every other difference. So many to none, many to one, and none to one. So it does do them in alphabetical order because that's the way R translates factored variables. Right? And so it tells me what's the difference between the two. So it's literally the subtraction of mean 1 minus mean 2. And then what's the p-value. So check these out. These are both significant right here, right now. So with no correction, many to one and many to none are, none to one are significant. And that is both of the 11 groups compared to the 9 group. Let's see what happens if we now start doing corrections. So we're going to do a Bonferroni. So it's the exact same code, actually. And we're going to use group equals false. Sorry, hit the caps lock key. Console is true. But in order to do p.adjust equals Bon for Bonferroni. Okay. So when I run that, it tells you right here, p-value adjustment method. So what Bonferroni does is it takes alpha, our 0.05, and divides it by the number of comparisons, and adjusts the critical score based on that. So if I have a new alpha for each comparison as 0.01666, because 0.05 divided by 3, that creates a new t-score, so a new cutoff score. And so if I scroll up here and look at no correction, it's 1.97. So basically, Bonferroni is sort of like your evil bad guy in Tom and Jerry movies, where he like picks up the finish line and moves it further out. And that's a good analogy for how most of these tests work. So it's a more restrictive t-value, the line you have to cross to say they're significantly different further away. And so now what you'll see is this is the only one that's significant. So that made our mean difference between none to 1 to 2 flip from being significant to not. So that is where the correction piece comes in. So it corrected our ability to find that test because maybe that's a type 1 error. Okay. What if instead I wanted to do, let's do student Newman-Coles. So the way this one works is it corrects by doing what's called a step-down procedure. And so what happens is it will find the largest difference between means and use one cutoff score. And then it finds the second largest difference between means and uses a less stringent cutoff score, and then it keeps going. And so it sort of stacks them and creates the most stringent score for the largest difference and the least stringent score for the smallest difference. Some people consider this sort of cheating, and that it will the type 1 error rate is inflated at the smaller differences, but it allows sort of like a step down. So as we get to smaller mean differences, it doesn't count these previous tests against you. And so you'll see on this one, now they're both significant. So student Newman-Coles is a little less stringent than Bonferroni. Bonferroni tends to be one of the more stringent tests, as well as Scheffe. Okay. And so by using that step-down procedure, those mean differences are so very small. So look up here. So I've got 0.04 and 0.08, and you'll see that the mean difference is almost the same, 1.35, 1.31. And so saying that one is significant and the other is not is sort of like being like, well, I mean, with their correction got unlucky. Or maybe they're both type 1 errors. Could go either way. But with Student-Newman-Cools, what it allows us to do is this critical range. So, like, here's the significant mean difference that I had to have for the largest difference, and here's the significant mean difference I had to have for one of the smaller differences, and that's why they're both significant. Okay, so 1.34 is greater than 1.32, so that gives me a p-value of 0.05, effectively, and 1.31 is greater than 1.11, or 10, and so that's why it's significant. So in this case, they're both significant. Okay. I don't think Student-Newman-Cools is very popular, but if you have a lot of means and you're trying to find the largest difference, you're sort of saying which groups have the biggest differences, it would be a good test. The most popular is definitely Tukey. So let's run that one. So Tukey corrects on the mean differences based on how many means you have. So while Student-Newman-Cools also corrects on mean differences, it corrects in a step-down way. Tukey looks at the number of means that you have and says, here's the new mean difference based on these number of means that you have in your study. So it corrects for the number of groups there are in the study. Alright, so we'll see that we have a critical value of what's called the studentized range. This is the Q statistic. It is not a t-value. It can be translated into t, though. And so these critical values change based on what type of correction we're running. And we'll see that this one is significant still, and this one's close. So closer than before with a Bonferroni correction, but still not significant. So marginally significant, which is what the little dot means. So you'll see that the correction matters. So picking a correction that makes sense for your data or your field is important. Let's do the last one is Scheffe's test. So Scheffe is a bit different. It runs mini ANOVAs instead of t-tests, or that's my understanding of it. I think in this output it's going to look like a t-value though. So let's get it. And what it does is it actually, no, okay, that was a different one. JK, never mind. So Scheffe actually is, the post hoc test is a one-way ANOVA with only 2 groups, and the correction is Scheffe. Scheffe was really popular for a long time, but most people think it's too stringent now. So it's not, it's too restrictive, especially with large groups. So large numbers of groups. What Scheffe does is it corrects for every possible complex comparison. So you could do all pairwise comparisons and all of the complex comparisons as well, meaning I could do 1 versus 2 and 3, or 3 versus 2 and 1. So it's actually correcting for other additional things rather than just the 2x2s. And so it tends to be a little too stringent for some people. Tukey tends to be the nice balance between too stringent, which is Bonferroni and Scheffe, and too loose, which would be analysis or no correction. Okay. And I haven't been writing this out here, so this is S and K for Student-Newman-Cools. This one is Tukey, although it says HSD in the front, which is honestly significant difference, and this is clearly Scheffe. Okay. So looking here, our many to 1 to 2 is significant, but none to 1 and 2 is sort of marginally significant. So that is a really great example of how these different tests correct in different ways. Okay. And you'll see that based on what it says here. So this is a new critical F score for 2 groups with 165 degrees of freedom. Okay, so 2 and 165 on a F table. But as you're running a real test, just do 1. Don't do a bunch. That was just for showing you how this works. Okay. But instead, our other option is that we could do a trend analysis. And so trend analyses look at how the data, how the groups might increase over time or decrease over time, or maybe make a curvilinear pattern. So this is a good way to test if our linearity assumption, if the linearity is bad, maybe run a trend analysis and see, oh, it is curvilinear, so I should do a different type of analysis rather than the straight regular ANOVA. And I cannot remember this off the top of my head. So what we're going to do is I'm going to copy this little piece of code here. All right, let's save this as output 2. So what happens is I'm going to set K here to the number of groups. And so that will allow me to change one piece of code at a time. Okay. So then what I'm going to do is create contrasts. Okay. So the contrast function allows me to sort of tell it to run in a different way without getting too crazy into it. So I'm going to use my no outliers data set because that's what I've been working on. And you do this on your IV. So this sets up the IV. And we're going to say specifically we want to do poly contrasts, which is what for the number of groups I have. So contrast.poly allows us to do trend analyses. So we're actually going to reset, and we could actually create a new variable here instead of resetting the variable, and create ourselves a new IV that is set up to run as trend analysis. So let me make it as a new IV instead of overwriting the original IV. Okay. Contrast only applies factor. Oh, if I'm going to do that, the first thing I have to do is this, is create the new IV first. So you can do it either way. You can overwrite the original, because I could just reload the data set. There we go. So now I have a new variable in there called coax2, and I want to make it a contrast variable, and so you'll see that that does some creates some new code out here that it understands that it's a contrast variable. And then what I'm going to do is run my ANOVA again. So I'm going to call this a different output 2. So AOV is, let's do, it's DV, so anxiety, is approximated by our new contrast variable. Data set equals no outliers. Okay. Coke2 not found. Did I put this in the wrong font? Coax with an S. There we go. Now we're going to do summary.lm for our variable, our new output. And what that does is it creates us a polynomial contrast, which is effectively trend analysis. So the coax2 here .l is linear, so a linear trend. Coax2.q here is a quadratic trend. And so what we would do is these are t values, so we'd look across here and look at p. And p is not significant. So this is a nonlinear trend, which is why our linearity graph looks so wacky. So I go back up here and rerun that graph again, and you'll see that this is problematic over here, right? So mostly it's a linear, but then we have these tails here that are problems. And so in running this output, it's clear that this is not a linear trend. It's a quadratic trend. So that's x squared. So, and that was pretty easy to see if you were looking at the means. So none to 1 to many to 1 to 2 to many creates this sort of U shape. And so I could actually probably better capture the data by saying this is a quadratic trend rather than doing a bunch of post hoc tests that may or may not capture that effect. So to do that, to portray that better, let's create a graph. Okay. And since I can never remember my own theme coding, I'm just going to copy it. Okay. I talk about this a lot in a bunch of other videos if you're interested, but this is the ggplot library. Okay. And I'm going to create myself this theme coding. So this is like my cleanup code. It helps clean up my graphs for me. And this time we could create this as a bar graph because it is a line graph because it is mildly continuous on the bottom. But I still think since this is very much dichotomous data, I'm going to create this as a bar graph because that's the more traditional style. But you could do this one as a line graph, just FYI. Okay. So let's create that bar graph. So ggplot of the data here, so no out. Aesthetics. What variables am I going to use? Let's see. I'm going to use coax and anxiety. So it's IV, comma, DV. Okay. If I did that backwards, we'll find out in a minute. So I'm going to say bar graph plus my theme coding. Oh, computer. There we go. Plus, now I got to add something to my bar graph. So let's do stat summary. So it's the function of y is mean, so give me bars that include the means. geom equals bar, so give me some bars. Right? Now we want to color those bars. So let's say the color of them is black. So that's the outside edges. And the fill is white. So that's the inside. I'm going to run all of that just to make sure I'm doing things correctly. Don't know how to add. Oh, great gracious. I forgot to run my themed coding. Do that a lot. Okay, here's some bars. Cool. So that's looking good. And here's that U shape. So that's why the quadratic was significant, is because of this U. Okay. So let's change up some other stuff. Let's add some error bars. Stat summary. Now it's a function of the data. Got ahead of myself there. Is mean, CL, normal, or you can do boot. Either way. Geom equals error bar. Okay. And this is where we have to get into positioning. So we're going to tell it to dodge, meaning don't lay on top of each other, but we're also going to tell it to control the width here, which I think generally I've been setting as 0.2. But just in case that looks funny, let's look at it real quick. Okay, those look like traditional error bars. So you can play with the width to determine how big you want it to be. Now I'm going to clean up the rest of the graph. So the X label is all sorts of bad. So number of Cokes drank, past tense, during the week, during the day. This is by day. Okay. Let's also add a better Y label. So see, these are extra descriptive labels. So average anxiety score, because that is what these are bars mean. Okay. My X-axis labels are also pretty terrible. So let's do its scale X discrete, because they are discrete. And then its labels equals, let's do none, so no Cokes, 1 to 2 Cokes, and 3 or more, just to make it look better. And then I could also change the length of the y-axis, because it does run up to 20, this scale. So I'm not creating a larger looking difference than is really there. So scale by continuous this time. And then it's lim or limbs. Limit? Can't remember. Let's try this one. 0 to 20. So let's see what I missed. Nothing. Yay. Okay. So that graph also looks a little funny because of the limit is 0 to 20, but you know, the average is way down here. But it does show you that the differences are rather small, because they are. They're only 1 point. 1 point here is a significant difference, depending on which t-test we look at, but it is not a huge difference. And so this would be a much prettier graph to present to someone. Now that really highlights the fact of I don't know what to believe about these differences. I've shown you that they are significant depending on which test. So I'm going to pick Tukey because I like Tukey. So I have these differences. This difference is significant, this one's marginal, but now I'm sort of stuck with what does that mean? So the last thing I want to finish with is effect size. So we're going to use mode because I'm partial to my own creations. Okay, and it's not going to pull up just for fun. Let's see if this is the right folder. Yay! Which you can download on my website. And coming soon to the internets near you as an online program. Under measures here, this is independent T, because this is a between subjects design, so I'm going to use the regular Cohen's D for independent T. I'm not going to correct with hedges, okay, but it could. And then I'm going to use this output right here to type in my numbers, or I could go back to my T apply means. So you do have to do this 3 times. So we've got many to none here. So I would do 11.16 to none, so 11.13. So this is going to be basically nothing. So then I got 275, 268, okay. And then my n values, so 67, 46. Okay. That'll actually give me the t statistic if I wanted to calculate it, but it's not corrected, so I don't know if I want to use that. Let's see here. It tells me the Cohen's D is 0.01. So that's like basically no difference between those means, which matches the statistic we found. So now let's do many to 1 to 2. So I got 11.16 to 9.82. So do at least 2 decimals. My 2.75 is an appropriate number. And let's change this to 3.31. 67 versus 55. Okay. And that implies my Cohen's d is 0.44. So it's close to a medium effect size. So one reason why it's significant. And then let's do none to 1 to 2. So I've got 11.13. That mean stays the same versus 2.68. Alright, and then 67, this should be 46 to 55. So gives me my t-value. So that's also a medium effect size. So I think I would have a hard time arguing that these differences, these mean differences, which are so similar, which have very similar effect sizes, 0.44 versus 0.43, are somehow, since one of them is significant, it's important, and since the other one is not significant, it's not important. So that's why effect sizes are so useful, is that they show me that these are basically the same effect. It's just depending on which correction I use, one of them is significant and one of them is not. So I'd really argue that they're both important because they're close to medium effect sizes, even if P doesn't quite line up with our magic line in the sand. And so, yes, I applied a correction, but I still think medium effect size is close to medium. It's something you should talk about, right? And it does create this quadratic loop. So there is something about drinking 1 Coke a day that's magic. Clearly I'm partial here. And so that would be a great thing to add to your report. And so the last thing that I'll finish with is, how do I report all this stuff? Definitely include a graph, because of course we just created this graph. Why wouldn't you include it? If I wanted to report the trend analysis, I could, but let's say I just want to do my regular ANOVA. So I'm going to go back to my summary for that output real quick. And so a report, I would talk about the mean differences or significant. So it's F, and the F is in italics because all statistical letters are in italics. And I would do the degrees of freedom. So 2, 165 over here equals the F statistic here in this column, so 3.84. My p-value, so p is 0.02, exact p-values are important. Then I would include r squared or eta, whatever letter you like better. I think eta is more traditional with ANOVAs, but I don't want to spend all my time finding the symbol on the keyboard because they are exactly the same thing. So if someone says, well, it should be eta, you should go, hey, the math is the same, it doesn't matter. Okay. And so my r squared one, I need my summary, oops, typing in the wrong window, of my LM, okay, which also has the same p-values and stuff down here. So 0.04, oops, sorry, 0.04. And then I would also want to report all of my t-tests. So let's go back to Tukey. So I would say I did independent t with a Tukey correction. Okay. To talk about my ANOVA, I would say it's a one-way between subjects, because that matters. It tells me it's more descriptive. ANOVA. Okay. All right. And then on this stuff you don't get T, which is unfortunate. But to report that, I would say that, many to none was not significant. I'd say my p-value, which is essentially 1, so 0.99, or you could say p equals 1.0. Some people might argue with you, but so our d value on that was 0.01. Okay. And then many to 1 was significant. Like these incomplete sentences, clearly. Our p-value is, oops, I hit underline there, 0.03, and our d-value was 0.44, so that's a medium effect. And then our none to 1 was marginally significant, if you can get away with it. P equals 0.07. But then really highlighting that the d-value is the same. So I really shouldn't treat these two as very different things, because the p-values are fairly close. The difference scores are fairly close, and the d-values are close. And really this P is being biased by the differences in standard deviation for those groups, especially because one group has a slightly larger standard deviation. Okay. So that's how you could write those up in APA style. Obviously in complete sentences, being more descriptive about what's going on, but then I would also include the picture. If you don't include the picture, be sure you include means and standard deviations or means and standard errors. And you also should probably tell people how many people are in each group. That would be in the participants section or in the beginning of the results descriptive sections, because they are not equal. And that does make a difference sometimes. So be sure to include that information somewhere. So all of that taken together is a very long way to talk about how to do data screening, power, effect size, and run an ANOVA with a post hoc test. So I showed you a couple of different types, trend analysis, and writing this up.